We may take its comforting glow for granted, but our moon is an unusual object in the solar system whose origins remain a mystery. Now there's a new theory to explain how it got where it is, and it involves a single, giant impact. The new theory appears to solve the enigma of why the moon is composed of such similar material to Earth, as well as explain its peculiar orbit. The theory is the brainchild of researchers at the University of California, Davis, and puts some twists on the original giant impact theory. The popular theory says that late in the formation of the solar system, in the giant impact phase when hot planet-sized objects collide with each other, a Mars-sized object grazed what would become Earth, throwing off a mass of material from which the moon condensed. This impact set the angular momentum for the Earth-Moon system and gave the early Earth a 5-hour day. Over millennia, the moon has receded from the Earth and the rotation has slowed to our current 24-hour day. Scientists worked this out by looking at the moon's current orbit and calculating how rapidly angular momentum of the Earth-Moon system has been transferred by the tidal forces between the two bodies, and working backwards. However, there are a couple of problems with the textbook theory, which the new version, published in the journal Nature, seeks to solve. One is the moon's surprisingly Earth-like composition. The satellite is made of almost the same materials as our own planet, minus some more volatile compounds that evaporated long ago. That makes it distinct from every other major object in the solar system, said Sarah Stewart, professor of Earth and Planetary Sciences at the University of California, Davis, and senior author on the paper. Every other body in the solar system has different chemistry, she said. Another problem with the original theory is that if the moon condensed from a disk of material rotating around Earth's equator, it should be in orbit over the equator. But the moon's current orbit is tilted 5 degrees off the equator, meaning some more energy must have been put in to move it. Professor Stewart, her former postdoctoral fellow Matija Cook, who is now a scientist at the SETI Institute, Douglas Hamilton at the University of Maryland, and Simon Locke of Harvard University, came up with an alternative model. In 2012, Dr. Cook and Professor Stewart proposed that some of the angular momentum of the Earth-Moon system could have been transferred to the Earth-Sun system, allowing for a more energetic collision at the beginning of the process. In the new model, a high-energy collision left a mass of vaporized and molten material from which the Earth and Moon formed. The Earth was set spinning with a 2-hour day, its axis pointing towards the Sun, and because the collision could have been more energetic than in the popular theory, the material from Earth and the impactor would have mixed together. So, both Earth and the Moon condensed from the same material, which explains why they have a similar composition. The researchers said that as angular momentum was dissipated through tidal forces, the Moon receded from the Earth until it reached a point called the Laplace plane transition, where the forces from the Earth on the Moon became less important than gravitational forces from the Sun. This caused some of the angular momentum of the Earth-Moon system to transfer to the Earth-Sun system. While this made no major difference to the Earth's orbit around the Sun, it did flip Earth upright. At this point, the models built by the team show the Moon orbiting Earth at a high angle, or inclination, to the equator. But over a few tens of million years, the Moon continued to slowly move away from Earth until it reached a second transition point, the Cassini transition, at which point the angle between the Moon's orbit and Earth's equator dropped to about 5 degrees, putting the Moon more or less in its current orbit. Professor Stewart believes the new theory elegantly explains the Moon's orbit and composition based on a single, giant impact at the beginning, with no extra intervening steps required to nudge things along.